Should I be describing this as one of my can we do that videos or one of my can we understand that videos? I don't know, but what I do know is that limits is often a topic that a lot of students view as being rather highbrow, unrelated to the world around us, but I'd argue against that, because limits play an important underpinning role in things such as calculus, which is really important for the world around us. And therefore, as part of trying to do calculus, some limits you might come across are ones such as these, because these two limits are important for doing the differentiation by first principles of both sine of x and cos of x. But how can we know what these limits come to? Well, that's why we're taking a look at something called squeeze theorem in today's video. And before we begin, I must give you the usual warning, which is this video covers things that you don't need to know for the A-level exams in England. But with that out of the way, I would like to begin by acknowledging that there are actually other ways of calculating these limits. For instance, the limit as h tends towards 0 of sine h over h could be calculated using series expansions. Or alternatively, if you prefer, small angle approximations, as those are pretty much just half-hearted series expansions anyway. But either way, that will lead you to a fraction that can then be simplified, and then you're in a situation where as h tends towards 0, all the terms with h in will disappear or effectively become 0, meaning you're just left with the number 1. Or alternatively, you could identify the fact that when we make h tend towards 0 for this fraction, the fraction is tending towards 0 over 0, which is of indeterminate form, meaning we could use L'Hopital's rule, which means we can then differentiate the top and the bottom of the fraction individually, meaning it's now in a format in which we can evaluate it, because as h tends towards 0, cos of h will tend towards 1, and 1 over 1 is just 1. Meaning, we've found the limit, which means we're done surely, we can end the video. But wait, there is arguably an issue with using either of those approaches on those two particular limits. And that's because if you're evaluating those limits by using either Maclaurin's series or L'Hopital's rule, you are making use of the derivatives of sine of x and cos of x, either directly in the case of L'Hopital's rule or indirectly in the case of Maclaurin's series, because Maclaurin's series is based on the idea that you're able to find the derivatives of the function you're representing using the Maclaurin series. But wait a minute, that's a problem, because the derivatives of sine of x and cos of x both rely on the limits of sine of h over h as h tends towards 0 and cos of h minus 1 over h. So that means we've got a circular argument, which is bad reasoning in mathematics. So we shouldn't do this. And that's why we're going to be making use of squeeze theorem, because it doesn't have this same issue as the other ones of having this circular argument. Squeeze theorem is also sometimes called sandwich theorem, but as talking about sandwiches for an entire video would just make me feel really hungry, I'm going to continue to only refer to it as squeeze theorem. But what are we actually trying to do here? Well, loosely speaking, squeeze theorem is this idea that you might have something that you're trying to calculate that you can put a lower bound for and an upper bound for. The problem is, if those bounds are too far apart, although you've narrowed things down a bit, there's still quite a bit of uncertainty about what precise value the thing you're calculating is actually meant to be. But if your lower bound and upper bound are actually limits themselves as well, and the lower bound is a limit that's calculated in a way so that it will actually start getting bigger, and the upper bound is also a limit that when calculated will start to get smaller, you might end up with a situation where the two bounds converge, meaning that the thing that's supposedly in between them actually now can only be one value, in this case x equals 4, and therefore you now know the value of that thing, even if at first it was appearing quite difficult to work with. So let's actually try and apply this concept to a limit. We could, for instance, try to calculate the limit as x tends towards 0 from the positive side of x lots of cos of 2 lots of x to the power of sine of x all divided by 5, and if the fact that trying to say that out loud was a bit of a pain isn't enough to tell you that this is some serious maths, you'll quickly realise it when you try and just plug in x equals 0 into this function, because it's undefined, because you've got a 0 to the power of 0 situation inside that trig function. But don't worry, squeeze theorem is going to help us out, because cos of x is a function that's going to output values that are between 1 and minus 1 for any x that's a real number. And we can extend that idea to the situation where you have more complicated algebra inside that cosine function, because as long as that function that's inside is still only giving out real values that we're inputting into the cosine function, it's still going to be between 1 and minus 1. Which is great news, as it means that cos of 2 lots of x to the power of sine of x must still be between 1 and minus 1, as long as we're dealing with x values greater than 0, because that will ensure we're dealing with real values. We're then allowed to multiply that function by x over 5, and because x is greater than 0, we're allowed to multiply the bounds in the inequality by that too, because x is a positive number, meaning we know this function must be less than or equal to 1/5 x, but greater or equal to minus 1/5 x, in other words minus 1 times by 1/5 x. That means if we're trying to calculate the limit as x tends towards 0 of our function, it's going to be a value that's less than the limit of 1/5 of x, as x tends towards 0, but greater or equal to the limit as x tends towards 0 of minus 1/5 x as well. But the good news is both of those limits acting as our bounds are both really easy to calculate. As x tends towards 0, 1/5 x will tend towards 0. And minus 1/5 x as x tends towards 0 is also going to be 0, meaning we know the limit of our function must equal 0. Admittedly, some of you might have been looking at that example and thinking, well, duh, of course it's going to become 0, because you might have noticed that that function had a factor of x, which means we can calculate specifically the limit of just x as x tends towards 0, which is just 0, and anything times by 0 is 0, right? But you do have to be careful, because here's another limit that's got x as a factor, and we're making x tends towards 0, so therefore you'd be forgiven for thinking this also tends towards 0. But no, it doesn't, because actually it tends to half. And so just to be clear, it's worth pointing out that you can only use that trick of taking some algebra out as a factor when calculating a limit if your two limits that you then split it up into are both finite. The only problem is with our example is we didn't calculate what that limit was individually, and although you could do it, the methods for calculating what that limit would be far more effort than just doing squeeze theorem anyway. Oh, and on a semi-related side note, the graph of the function we're just trying to calculate the limit for looks like this, which I personally think looks pretty cool, particularly when you start looking at each of these little sections that make it up, because for instance this section has 12 maximum points, whereas this section has 16 maximum points, and in fact the number of maximum points in each of these local areas goes up by 4 every single time you go across. You're welcome to count them if you don't believe me, but there you go. And therefore, yes, we can just look at the graph to confirm that the limit is 0. But the thing I really wanted to show you is that the graph can also give you a visual representation of what squeeze theorem is doing as well. Because if we look at the graph, we can see that it's bounded from above by the straight line of y equals 1/5 x, and bounded below by the graph of minus 1/5 x. And therefore, as all three graphs tend towards 0, we can see that squeezing effect take place with those two graphs both tending towards the same point, and therefore the graph in between the two of them must be therefore doing the same thing. But now that we have an understanding of what squeeze theorem does, let's try and use it to work out the limits as h tends towards 0 of sine of h over h and cos of h minus 1 divided by h. But we're not going to be able to do exactly the same approach we had before, because if you do, you'll quickly realise there's not enough squeezing. Is that even the correct word I can use? But anyway, you'll see what I mean in a few moments, but what we do know is that the function of sine of x is also a function that must be between 1 and minus 1 for all values of x that are real. And therefore we could find the function of sine of x over x as being between 1 over x and minus 1 over x, as long as x is greater than 0, so the inequality signs are preserved, because we're only dividing by a positive quantity. The only problem is that then when you try to calculate the limit as x tends towards 0 of all these things, the limit as x tends towards 0 from the positive side of 1 over x is tending to infinity, and the minus 1 over x would tend to minus infinity, which does lead to a fact that is true, but not entirely helpful, because it basically tells us that the limit of our function could be practically any value in the world. Yeah, great. So instead, we're going to be making use of a geometrical approach with squeeze theorem to help us calculate this limit, by looking at this sector. This sector, we're going to say, has a radius of 1 and an angle of x, where x is a positive number measured in radians. We're then going to be comparing that sector to a triangle formed by drawing a tangent from the bottom of the sector, therefore going directly up, and then joining that up to the radius of the sector extended to meet it. Looking at the diagram, we can then clearly see that the area of the sector must be less than or equal to the area of the triangle. And those are both things we can then calculate. For instance, the area of the sector is going to be worked out as half lots of the radius squared times by the angle. So that's going to simplify to 1/2 x. And then meanwhile, the area of the triangle is going to be calculated by using the fact that the base is the radius, so we already know it's a length of 1, and then using trigonometry with that angle and that base to get that the height of the triangle is tan of x. Therefore meaning the area of the triangle is 1/2 lots of 1 lots of tan of x. That then tells us that x must be less than or equal to tan of x, but tan of x can also be rewritten as sine of x over cos of x. And if we then say that x is between 0 and pi over 2, something we're allowed to do because we already pointed out that x was greater than 0, and x is less than pi over 2 is allowed to be said, because ultimately we're only doing this stuff so we can do the limit as x tends towards 0, so therefore the fact it's below pi over 2 isn't a problem. But that's important because it means that cos of x must be a positive number, which means we can multiply both sides of the inequality by it while maintaining the inequality sign. We could then divide both sides by x because x is bigger than 0, as we already pointed out, meaning that therefore the limit of sine of x over x as x tends towards 0 from the positive side must be greater or equal to the limit of cos of x. So therefore we've got a lower bound. But what about an upper bound? Well, that's going to be actually a lot easier to calculate, and there's several different ways you could go about it. Some people would prefer to do it by comparing the area of the sector to the area of this triangle, meaning we've got that half sine of x cos of x is less than or equal to half of x. Or alternatively, you could compare the area of this triangle to the area of the sector, meaning you would end up with this inequality instead. But my personal favourite way, because it's the easiest in my opinion, is to just simply draw a line that looks like this on your diagram. And that's because we could then quite simply work out the length of this arc by doing the radius times by the angle, and then we could also work out the length of this line, because it's just going to be the height of the triangle. And therefore, as we know the hypotenuse is 1, therefore the height would be sine of x. But we can see that the length of the arc visually must be longer than the length of the line, because the line is the shortest way to get from the vertex at the top to that straight line at the bottom. So therefore we have the simple inequality that sine of x is less than or equal to x. But then if x is greater than 0, that means we know that sine of x over x must be less than or equal to 1. So therefore, if we're trying to calculate the limit of sine of x over x as x tends towards 0, we have this. And then calculating the limit for that lower bound, well, cos of x as x tends towards 0 just tends towards 1. Therefore meaning that the limit of sine of x over x as x tends towards 0 from the positive side must be 1. And in my opinion, that's pretty neat, because ultimately we were able to calculate this limit by using pretty simple maths. And therefore, if you've liked what we've done so far in the video, please do remember to subscribe to the channel, like the video, and turn notifications on, because currently less than 7% of the people subscribed to this channel are actually being told when I'm releasing these videos. But we're not done yet for this video, because I did promise that we'd calculate the limit of cos of h minus 1 divided by h as h tends towards 0. So to do that, let's once again start by looking at the function, because we know that cos of x is between 1 and minus 1. This wasn't a really helpful avenue to go down with the other limit, but you'll see there is something useful here, because we could take away 1 from both sides, therefore meaning that cos of x minus 1 is between minus 2 and 0, and then we could divide everything in this inequality by x, as long as x is greater than 0. And that's kinda cool, because now if we try to take the limit as x tends towards 0 from the positive side of all three of these functions, although the left hand side doesn't provide us with anything useful because the limit of that tends towards negative infinity, the right hand side did come up with something useful because we know that it's bounded by 0. So therefore all we need to now do is work out a better alternative way of giving a lower bound for this limit. So to do that, let's take a look at that diagram we've already been using, because now we're going to connect up the two corners of the sector using a straight line, which means we've got a triangle, but crucially it's a triangle for which we already know two of the lengths of the sides, because two of its sides are each a radius of this sector that we already said earlier were a length of 1. Let's call this new third side a length of y. and we could work out the length of y by using cosine rule, which I've now written on the screen. Simplifying that, you're going to get 2 minus 2 cos of x. We can then compare this side length of y to the arc length that we already calculated earlier as being x, because we can see from the diagram that that arc length must be bigger than the length of that straight line, so therefore x must be greater or equal to y. But as both these are side lengths, they're both values greater than 0, which allows us to do the trick of squaring both things in the inequality, something you normally wouldn't be able to do because you're unsure if your algebra letters could be negative, but in this case it means we know that x squared is greater or equal to y squared, because squaring positive numbers is a strictly increasing function. Therefore, replacing y squared with the expression we calculated for it, we have the inequality that x squared is greater or equal to 2 minus 2 cos of x, as long as x is greater than 0. Therefore, we can multiply both sides of the inequality by minus 1, which does mean we have to flip the inequality sign around. We can then divide both sides of the inequality by 2, and then divide both sides of the inequality by x, because we already established that x is greater than 0. Therefore meaning we now have a function that we can use as our lower bound for our limit. And so therefore we can now calculate the limit as x tends towards 0 from the positive side of minus x over 2, which comes to 0, meaning we now know the limit as x tends towards 0 from the positive side of cos of x minus 1 over x is equal to 0. Now admittedly we did do both these limits by only doing x tending towards 0 from the positive side, and that's just because that was easier to show if we're doing this stuff geometrically. But you could also prove this same stuff with x tending towards 0 from the negative side, still doing it geometrically, but you just have to have the sector with an angle that's been measured clockwise rather than anti-clockwise, and therefore the heights of the triangle etc would be expressed as negative quantities. But the thing is, these aren't the only awkward limits you have to encounter when trying to do differentiation by first principles for the elementary functions. For instance, when you're trying to do differentiation by first principles for e to the power of x, you have to evaluate this limit. And what's it going to come to? Well, as a little bonus, let's calculate it for you using squeeze theorem, because did you know that e to the x is greater or equal to x plus 1 for all real x values, both from looking at the graph where you can see that it is greater than it, but also just from the fact that x plus 1 is a tangent to e to the x at the point x equals 0, and therefore only intersects with it once, but because of the way e to the x curves, it's going to curve away from it and therefore will always be above. Therefore, utilising this fact, we could start by taking away 1 from both sides of this inequality, and then as long as h is greater than 0, we can divide both sides by h, meaning that e to the h minus 1 divided by h is always greater or equal to 1. So that's the lower bound for our function sorted, but what about the upper bound? Well, to do that, we're going to use a little trick, because we're going to reflect both the graphs we had before in the y-axis, meaning we'll have something that looks like this. But in terms of what happens to the algebra, e to the h will become e to the minus h, and h plus 1 will become minus h plus 1, meaning we have the inequality minus h plus 1 must be less than or equal to e to the minus h. So, making use of this fact, we could first just start by writing it in a nicer format, such as this, because then we could realise we could start by multiplying both sides by e to the h, because e to the h is always a positive quantity. And then we could divide both sides by 1 minus h, as long as h is less than 1. Again, we're allowed to put that restriction on, because ultimately we know we're going to make h tend towards 0 anyway, so having that upper bound on what h can be isn't a problem. And so then we could take away 1 from both sides, and then do a bit of algebra rewriting, because that right hand side could be rewritten as this, combining the two fractions means we've got this, and then we could also divide both sides of this inequality by h, as long as h is greater than 0. So therefore, as long as h is between 0 and 1, we now know that e to the h minus 1 divided by h is going to be between these two functions. The lower bound we calculated earlier is already set in stone as being the number 1, but the upper bound, if you calculate that limit, will also come to 1, therefore meaning the limit is 1. The only question that some of you might be asking though is how can we actually justify that e to the h is definitely greater or equal to h plus 1? I did mention that it was a tangent, which you could see visually, but algebraically proving it's a tangent is going to be kind of difficult unless you use differentiation, and we kind of already pointed out that's a bit of a circular argument. So how can we do it without using differentiation? Well, there is a way by going back to understanding what the number e actually is and where it comes from. But if you're going to all of that hassle, there is a much easier way of doing this limit in general. And so therefore, I am actually going to cover that in a future prove it video, proving the derivative of e to the x from first principles. So do watch out for that. But the last question I want to leave you with is whether squeeze theorem is only useful for calculating limits as part of differentiation by first principles. Well, the answer to that is no, because interestingly, squeeze theorem can also be used to help us do integration by first principles, and funny enough, that is going to be the next video in my Can We Do That series, so stay tuned for that. And with all that said, that's all I want to cover in today's video. I am actually going to do another video in 3 days time showing an alternative way to calculate the limit of cos of h minus 1 over h using squeeze theorem, so stay tuned for that. But also, I've got a whole playlist of the Can We Do That series so far, link to that is appearing on the screen right now. Goodbye!